Okay, so today I'm going to start by discussing elementary properties, definitions, and so on of Kac-Moody algebras. So we'll begin with the definition again of a generalized Cartan matrix. So definition. So we say that A is a generalized Cartan matrix. So it's a square matrix, so it's n by n. If it satisfies the following. So the diagonal entries have to be 2. The off-diagonal entries are non-negative integers. And the zeros must occur symmetrically. So we'll limit ourselves to symmetrizable generalized Cartan matrices. So what that means is there exists a diagonal matrix.
Just to remind you.
Yeah.
It's bigger.
Diagonal matrix, di, such that the matrix di aij is symmetric. Okay. So associated to this data, Katz and Moody define the Kac-Moody Lie algebra, so GA. So it's a Lie algebra with 3n generators, which we'll write as xi plus or minus hi, and some relations. Okay. So the relations are pretty much what you would expect. So the hi's must commute. The xi plus and the xj minus, well, it's 0 if I is not equal to j, and otherwise it's hi. You need a relation which says that hi, that the xj plus or minus are eigenvectors for the hi, so that's plus or minus aij xi plus or minus. And the fourth relation is called the Serre relations, because they were originally shown by Serre to give you finite dimensional simple Lie algebras, and that we'll write as follows: summation r equal to 0 to 1 minus aij. It's xi power r. I'll tell you what that is in a minute.
So, is that an xj or an xi?
I'm going to write this more xj, thank you. So this is xi plus or minus all raised to r, xj, xi plus or minus 1 minus aij minus r equal to 0. So this is why we're really using that the off-diagonal entries are less than or equal to 0. When we write 1 minus aij, it's actually a positive number. And what does this mean? So this is a notation. So if you take an element x, and what do we mean by x to the r? You mean x to the r divided by r factorial. Okay. This is the same as saying is equal to the adjoint of xi plus or minus raised to 1 minus aij xj plus or minus equal to 0. Are you puzzled by something?
Yeah. So the meaning of this when you write multiplicating these?
Well, so this will be an identity in the enveloping algebra. Yeah. So you can think of this as so if you want to write it in the Lie algebra, you write it like that. Otherwise, you think of this as an identity in UG. So I'm writing it like this because in the quantum case, this is what I'm writing. Okay, so this is called So this is called the Kac-Moody algebra. This is not the definition that you'll see in a typical textbook, and I'll explain why you don't see that in the typical textbook in a minute. So this was the original definition. So why is the modern definition a bit different? Once you have this, you want to define a set of roots. So you want to you imitate everything that goes on in the simple Lie algebra. So what is our Karsen Lie algebra going to be? It's going to be H equal to summation I equal to 1 to n C of Hi. Yeah. What is n plus or n minus going to be? This is going to be the subalgebra generated.
The definition of Aij, could you recall please?
Aij is, yeah, I might get my transposers wrong.
Yeah.
Should I have Aji here?
Looks like, yeah.
Okay.
Given what you find it.
Yeah, I'm never sure. Okay, but this is correct to be Aij.
Redefine your Aij is the other. I mean, you then have to also switch it in this.
That's what I'm asking. Should I switch it here as well? I don't remember. So these formulas should be taken with a pinch of salt. I might be working with the transposer matrix from time to time, but it doesn't really affect the, yeah, so pinch of salt. Okay, it doesn't seriously affect the presentation, but so indices are a problem always. So this is going to be the subalgebra generated by the elements xi plus or minus, and then it was shown that you can write GA as the sum of these three subalgebras as vector spaces only. Okay, so far it goes along like it did in the case of simple Lie algebras. So then what would we want to do? We would want to define simple roots. Okay, and the simple roots for the simple Lie algebras are given by the Karsen matrix. So that means we would want to define alpha I on Hj, and now I'm nervous, but I'm still going to, so what have I got over there? Now I think it's okay, and so I will write Aij. It's consistent with the change that I made over there. Okay? And so we define this for 1 less than or equal to Ij less than or equal to n. Yep. Now when you're working with simple Lie algebras, what's the point about this simple roots? The point is that they're linearly independent. They're a linearly independent subset of H star. Okay? And why are they linearly independent? It's because the Karsen matrix is non-singular. Right? So the alpha i's for Kac-Moody algebras need not be linearly independent. In fact, they are not linearly independent if determinant is 0. Okay. And the determinant can be very easily 0. So in the simplest example, so let's write down, I should have done this. Let's write down a simple example of generalized Karsen matrices. So the simplest example of a generalized Karsen matrix. Well, the most trivial example would be a 1 by 1 matrix, right? In which case you have no choice but for it to be 2. Because the diagonal entries have to be 2. So what's the next choice that could be non-trivial? It's a 2 by 2 matrix. Right? And what are the only restrictions we impose? You want 2 over there on the diagonals, right? And you want non-zero, and obviously if you put 0 over here, that's still not interesting. Suppose if I take this, then this is the Karsen matrix of what? SL2 direct sum SL2. So let's take a slightly more interesting example. So let's take 2, 2, minus 1, minus 1. Yeah? What is this, the Karsen matrix? This is actually, now if you look at this is actually a Karsen matrix, and it's a Karsen matrix of SL3. Okay? This is the Karsen matrix of SL3. Okay? So this is something you should be able to check. It's an exercise. And so here's our first non-trivial example. 2 minus 2 minus 2, 2. No, it's okay. It's out of the way. Right? So we needed our diagonal entries to be 2. Our off diagonal entries are negative integers, and that's the only condition, right? And if you notice also, if you look at a principal minor, what you get is just 2, right? And that is the Karsen matrix of SL2. So this is an example. So this is an affine Karsen matrix, which I defined yesterday, and the determinant of this matrix is 0. Okay. So it's trivial to find examples, interesting examples where the determinant is 0. But so to go back here, one really doesn't like simple roots being not linearly independent, because many of the arguments you see in simple algebras uses the fact that simple roots are linearly independent, right? So that's why there's a simple trick to force it to be linearly independent. You just make your Kac-Moody algebra a bit bigger. So what you do is, to make the alpha i's linearly independent, you enlarge your Kac-Moody algebra slightly. So you give yourself an additional vector space. It used to be called the extended Kac-Moody algebra, so I'm going to stick with that notation. So you take the original Kac-Moody, and then you give yourself an extra vector space of dimension s, where s is equal to n minus the rank of A. Is there a question? Okay, so you increase the thing, and you take a basis for this, d1 up to ds, okay, and you define HEA. So yeah, I should tell you, right. So what is so at the moment these are just vector spaces, right? So I have to make this into a Lie algebra, so I have to tell you what the commutator of something here with something here is. I don't change the commutator here, and that I'm going to just decide that di on 8j is 0, so I force it to be commutative, and then di on xj plus or minus will be equal to delta ij xj plus or minus. I should have a plus or minus here. Okay. So now I can just erase this, and now I'll change my definition of simple roots. So I'll have that, and I'll say that alpha I on dj is delta ij. So it's a very cheap trick, and the effect of this cheap trick is that the alpha i's are now linearly independent. So the alpha i's are linearly independent elements, not of H still, but or its dual, but of H direct sum CS dual. Okay. So this is what is nowadays called the Kac-Moody algebra. They build this extra piece into the definition of the Kac-Moody algebra. So that's our definition. So you can see it's horribly abstract. Where are my glasses? And one of the reasons that Kac-Moody algebras, one doesn't usually study Kac-Moody algebras in great detail. So little is known even now about the structure of a general Kac-Moody algebra. So what do I mean by that? So what kinds of things would one like to know? What does one know about simple Lie algebras, for instance? So for simple Lie algebras, one knows the dimension of the root spaces, for instance, right? You know that all the root spaces are one-dimensional. You know lots of structure, you know lots of properties about the root system, you know, and so on. So let's see. So how would we define? So Kac-Moody algebras have. So I've already defined n plus. So Kac-Moody algebras have root spaces alpha, which will live in this in the dual of the extended Cartan. I've defined the extended Cartan. No. So the extended Cartan will be HE equal to H direct sum C to the S. Okay. So that means so you can define G alpha to be the set of all elements X in G such that H bracket X equal to alpha HX. Simple Lie algebra's dimension G alpha is 1. For Kac-Moody algebras, it's known that dimension G alpha can be bigger than 1. Right? But it's certainly not known what the dimensions are. Right? No, I mean, even bounds are not known. Okay? But not much else is known generally, except for affine cases. Except in the affine case. So there are some examples where you know some things. They're called hyperbolic Lie algebras and so on. But in general, not much is known about them. So, and these were originally defined, I don't know, in the late 60s. So, and still virtually nothing is known about the structure of these Kac-Moody algebras. Okay? So this is another, so I'm trying to motivate why one might want to always restrict one's attention to affine algebras. It's because one just doesn't know anything in the other cases. Okay? All right. So since I'm doing generators and relations, let me also tell you what the quantum Kac-Moody algebras are. So the definition is very similar, so this might be a reasonable place to do it. Okay. So these quantum algebras are supposed to be deformations in some way of Kac-Moody algebras. Actually, not of the Lie algebra, but of the enveloping algebra. So we're going to write this as UQ of GA. So this is an algebra. There are two ways of thinking of it. So it's an associative algebra. You can think of it either as being defined over the rational field of rational functions in a variable Q. So Q is an indeterminate. Or you can think of it over C. So you can also think of it as an algebra over C, where Q is now thought of as a non-zero complex number. Okay. Both are possible. So it's generated. So it will have our favorite number of generators. So by elements, I'm going to use capital letters. So it's xi plus or minus, ki plus or minus 1, 1 less than or equal to I less than or equal to n. N is the rank of our GCM. So it's not very difficult to write down these relations. So of course the ki's will commute, and they'll commute with the inverses as well. So imagine putting plus or minus 1s. The xi plus bracket xj minus. So it's supposed to be a deformation. Now, if you were working in the simple algebra, you would have said that this is just delta ij times hi, right? So over here, it's still delta ij. But you don't see any hi in this definition. What you see are these ki. So that has to somehow come in. And so this, that comes in as follows. Ki minus ki inverse over q to the di's. Remember that these di's were what made your Karsen matrix symmetric. Minus q to the minus di. Okay. So ki. Okay, so then there was a relation between h's and x's. So now that relation becomes a relation between ki and x's, and that's that. Q to the di, oh dear, aji, xj plus or minus. And the Serre relation. So you should really compare it with the defining relations of G, and you'll see it's not so very different. And so the Serre relation, well again, so I want to write it like this, r equal to 0 to 1 minus aij, xi plus or minus raised to r, xj plus or minus raised to, so 1 minus aij, oh, that should, I'll change that to that. And in between here, there's an xj plus or minus. Now, this r that I had when I was doing Kac-Moody algebras, what was this? This was just, let's drop that. This is just xi to the r divided by r factorial, okay? But when you're doing quantum, you can't do much about this. You can't really, since q is an indeterminate or a complex number, you don't do anything with this. But this is, when you're thinking of this as an integer, you replace it by what is called a q integer. So that means that quantum r, by definition, is q to the r minus q to the minus r divided by q minus q inverse. Okay. So if you're thinking of q as a complex number, there's no problem with this. Otherwise, you're dividing by a polynomial. Notice that q minus q inverse divides it, and that's why we're working over the field of rational functions. Yeah?
And you have to appropriately restrict q's and c's so that none of these denominators are zero.
Yeah, q, we'll say q's and c's star. Well, yeah, and q not a root of, let's just assume q not a root of unity. Yeah, you have to. Okay. And here, yeah, so actually we have to put in the subscript. So it's very inconvenient to have non-symmetrizable matrices. So this is all that. But anyway, so everything is abstract. Everything is given in these terms of terrible generators and relations, and it's hard to get your hands on them. But still, it's possible to do lots of things with these algebras. So the other important thing is that UQ of GA. So I want to make this comment over here is Hopf algebra. Now we discussed briefly what a Hopf algebra was. It has a co-multiplication, co-unit, and then antipode. Yeah? I'm only going to tell you what the co-multiplication is. You can find all the other definitions in any book. So delta on xi plus, so here, so let me write this down. So this is xi plus tensor ki plus 1 tensor xi. Okay. And if you do it on xi minus, it's xi plus minus tensor 1 plus ki inverse tensor xi. And on ki, it's ki tensor ki. So there's something very important that you should notice when you see these formulas. So there is a notion, so you know what a commutative algebra is, right? AB equal to BA. What is a co-commutative Hopf algebra? So what does co-commutative mean? It means if you switch the order of the co-multiplication, right, then it should be the same. So let me tell, so co-commutative Hopf algebra. So co-commutative Hopf algebra is the following. So suppose
K cross 1 plus 1 cross K.
no, that's the whole point. It's group-like.
Group-like.
Yeah, it's group-like. Because Ki is invertible. So what is a co-commutative Hopf algebra? So supposing we had our Hopf algebra A, and you have your co-multiplication A to A tensor A. Okay? So you should think of this as always as reversing arrows. So the multiplication would have gone like this, right? So if you think of it as reversing arrows, then what you have to do is you take the flip map. Yeah. So this is A tensor B going to B tensor A. And co-commutative would mean that sigma composed with delta equal to delta. So if you change all your arrows, you'll see it means exactly that your multiplication is commutative. So this is the dual notion, if you go backwards. So UG is co-commutative. The deformed algebra is not. Okay? So UG is co-commutative. UQG is not. Right? Because if I flip it, this is going to give me Ki tensor Xi. Right? And Xi tensor 1, so it's not. So this is what makes quantum algebras very interesting. So one consequence, so what were Hopf algebras good for? They're good for defining tensor products, right? As far as I'm concerned. So if you had a co-commutative Hopf algebra, then what you have is a canonical isomorphism from this. And this map would just be this. Is an isomorphism of modules. Okay. So the canonical map gives you an isomorphism. This is false for quantum algebras. So this is false for UQG. However, in many cases it is true, so it does remain true. So it does remain true sometimes that V tensor W is isomorphic to W tensor V, but not through that map, but this is through another thing, another gadget, which is called the R matrix, but I'm not venturing there. But this R matrix is something that works well only for simple Lie algebras. So we're going to see examples where this is just not true. So for UQGA, there will be examples, there are many examples, and that's what again makes the representation theory very interesting, whether so it's not that I don't know that there isn't an isomorphism, I can prove that there does not exist any isomorphism between so there are examples of V and W where you don't have such isomorphism. So this R matrix is not an, yeah. Did you have a question?
Are these going to be the cases where these tensors are simple?
Yeah.
Or would these precisely be those cases?
Oh, no, if the tensors are simple, if V tensor W and W tensor V are both simple, then they will be isomorphic. But it's precisely when they're not simple. So one is cyclic and the other will not be, and so you'll have, yeah. For finite dimensional representations, yeah. Mm-hmm. Okay. Okay, so this is a little diversion into quantum algebras and how they're different from Kac-Moody, from the non-quantum case. So much of the motivation for what we're going to talk about later comes from the quantum case, so it's useful to keep building it in. Okay. Right, so now I'm going to go back, so I've defined my simple roots. Right. Okay, so now I'm going to go back to my Kac-Moody algebras and tell you some more interesting differences. So, we need another. So A is a generalized Cartan matrix. So one result that I should have stated earlier, which you can think of as the theorem of Serre, is that the dimension of GA, the Kac-Moody algebra, is finite if and only if A is a Cartan matrix. Okay, so I think to make my life simpler, I'm going to use simple when I mean a Cartan matrix, and when I say a Kac-Moody algebra, I'm going to mean that it's infinite dimensional. Okay, just so that it's, I don't have to keep saying that it's not a Cartan matrix. So let me recall something that we did yesterday. So when G is simple, we defined what we call the highest root, an element theta in R plus called the highest root. And what did we need to define it? We needed a partial order, right? And then we took the maximal element with respect to that partial order. Okay, so what do we do in the Kac-Moody case? Well, we still have, we have our simple system. So let me continue to call this pi, which is alpha 1 up to alpha n. So now I'm in the Kac-Moody case. I can still formally define fundamental weights, which I'll call omega 1 up to omega n. And this time they're going to be defined not by using the killing form. So once you have an infinite dimensional algebra, you don't have a nice analog. You can't define the killing form in the traditional way, right? Because it was add x, add y, and add is an infinite. Now add x is an infinite dimensional matrix. But so you can just do it in a straightforward way, which is you just say omega I of hj is delta ij, and omega I doesn't see your specious additional things that you put in. These really are just a device to make your simple roots linearly independent. Okay. So then we have no problem defining weight lattice and root lattice. Root lattice is the z-span of the alpha i's, and the weight lattice is the z-span of the omega i's. And as before, P is contained in Q, and we have our partial order less than or equal to. So you have lambda less than or equal to mu if and only if mu minus lambda is in the z plus span of the alpha i's. But here's an important fact which underlies, again, much of what we're going to see. Lemma. I'd like to say it's trivial to prove, but I couldn't write to prove. So there does not exist a maximal order, maximal element in R plus with respect to less than or equal to if dimension GA is infinite. That means if you take any root, any positive root, you can add some simple root to it and get a bigger root. Okay? And this again, so again you have to believe that you can define an analog of the while group. So another lemma which is false. So if you're doing a course in semi-simple Lie algebras, what is one of the results you prove? You prove that any root is W conjugate to a simple root. Right? That's one of your basic lemmas. So that's false over here. So for Kac-Moody algebras, there exist roots alpha such that alpha is not W conjugate. So you have to take it on faith at this point that many of the things that you can define for simple Lie algebras, you can also define for Kac-Moody algebras. So you have a notion of while group and everything. It's just that some properties fail you. So it's not W conjugate to a simple root. And such roots are called imaginary roots. These are called imaginary roots. And it's this so if you remember, I said a little while earlier that you don't know much about the structure of Kac-Moody algebras. And why is it that you don't know for the most part? It's because you don't, these imaginary roots are what cause problems. Everything else is relatively well behaved. But these imaginary roots are hugely problematic for general Kac-Moody algebras. Okay? So this is the problem with that. Okay. It's still amazing how much you can do in general. But you always have to work around these issues. Okay. So, let's see. Okay, so what I want to talk about after this is the representation theory, so this might be a good place to take a short break, I think. Or if there are any questions, I'm happy to answer them at this point. But focus of the next part will be on representation.
You automatically use the decays to mean both those extra dimensions and the symmetrizing matrix.
Oh. Yeah.
Should not be any confusion.
Right. Is that, yeah. So, so I had my CS and I had these things over here which were supposed to be bases for this thing, but I also had another definition of the D's as the integers which made your matrix symmetrizable. But
you can't confuse integers with vectors, that's okay.
No, but
yeah.
Could you shed some light on the uniqueness or so the rigidity of the quantum group definitions? Is there some principle behind that you can only deform it so and not?
No. So what is the principle? So the idea is that you want to, so you would like to deform the Lie algebra. You can't because it's rigid, right? So you choose to deform the enveloping algebra. And you want to deform it as a Hopf algebra, okay? And then, so what do you want to happen? When you sort of send Q to 1, you want the multiplication to go to the multiplication and all the Hopf algebra structures to go to the corresponding Hopf algebra structures. Okay, so the only rule, so there is some abstract thing, and the only rule that you have is, so supposing you want to, it's hard to do everything over Q, but if you work over a power series ring, and if you call this co-multiplication delta H, you sort of want delta H to begin like delta, okay, and then you want a first order deformation, and then you sort of don't care about the others in some sense. And so this first order deformation you control by what is called a bi-algebra structure on your Lie algebra. Yeah. It's been a while since I've had to justify this. This first order term reflects a bialgebra structure on G. So it's not actually on your Lie algebra, it's not actually on your enveloping algebra, it's actually on G. So what is a bialgebra? It's a map from G to G tensor G which has to satisfy certain properties. So when you're actually when you're deforming, so if you're just asking how to deform a Lie algebra, you have to specify what the bialgebra structure is. So then you want your co-multiplication to be nice over here. This should reflect delta, and then you sort of don't worry too much about the rest. So when we're talking about the quantum Kac-Moody algebra associated to a particular Karsen matrix, you're fixing a particular bialgebra structure. That's what I can tell you. I think there are a series of papers of Ettinghoff and maybe Karsen which address, which answer some of these things.
So it's kind of well understood now that these are the only ways.
I mean, so what is your, so the question is, so what you're asking me, supposing you give me a Lie algebra and you're giving me a co-cycle, is there a unique way to do this? I don't know how to answer. I don't know how well formulated such a question is.
Probably irrelevant.
Yeah, I mean, so the point is that, yeah, one doesn't necessarily go into this level of abstraction. This question is what is important to the thing. Yeah.
Does this construction also work in the Affiant case? The formula for delta H?
Oh, this is supposed to work in general. This is what you mean. So there's some general notion of what you mean by deformation of a universal enveloping algebra. So you just say that it's a deformation of an enveloping algebra. If you have so if you want to deform UG, then you're looking for a algebra UHG, such that as H goes to 0, this becomes UG. And you want the co-multiplication to have this property so that the first order terms come from delta. Exactly.
No, because I think in your book you've got a formula for this identification.
That's right.
In the case of, say, the quantum group of SL2, but you're saying even in the Affiant SL2.
Well, I don't know that you know this even for general G, right? What the exact identification is. It's only known for SL2, I think. This is just a general principle. For the most part, nobody cares about these questions anymore because you've identified what's, for the most part. But you've identified what's, so the interesting thing is that I haven't thought about this kind of question in a long time. But in principle, this is always what you mean by a deformation. And what we have are, so the algebras we're thinking of are examples of this. And I would have to inspect the papers of Karsen and Ettinghoff to see what they actually prove in that. But so, I mean, yeah.
Suppose the Hopf algebra is a star Hopf algebra.
Yeah.
Is it still true that there are cases where delta and delta of Hopf are not related by an R matrix?
I don't know what a star Hopf algebra is at the moment.
Star operation preserved by delta.
I don't know. See, even in the affine case, there is a Karsen matrix. The problem is, I mean, there is an R matrix. The problem is not that it's not that it doesn't exist, but that it's not well behaved with respect to finite dimensional representations.
Second question is quasi-Hopf algebras have turned up in physics.
Yeah.
Do they have some kind of Kac-Moody underlying them?
Quasi-Hopf algebras. Oh. I would have to think about that. I would have to look. I think there might be. I don't know if they're Kac-Moody algebras exactly. I would have to look.
Something like some generalization.
Yeah. I don't know the answer offhand. So let me start with some representation theory. So okay. So So what's the most obvious representation of a Lie algebra? It's the adjoint representation. So let's write the first example. So there's the adjoint representation of GA. Okay. How do we construct more examples? We always imitate. And so you construct examples by seeing what you do for simple Lie algebras. And what do you do for simple Lie algebras? You start with something with an element which lives in, so I'm going to use this extended notion, in the dual, right? And then you define what we call the Verma module. So you define the Verma module, which is m lambda. And how do we define that? We take the enveloping algebra of GA, and you quotient out by some obvious relations, which is h minus lambda h and n plus. Okay, and you have to believe that everything works exactly like it does in the simple case, and you prove the following proposition. You prove that m lambda has a unique irreducible quotient. So it's for statements like this that you want unique irreducible quotients and so on, that you really want to extend your affine Lie algebra. Otherwise you won't have that if you're Kac-Moody algebra. Otherwise you won't have linear independence, which is critical for this. It has a unique irreducible quotient, V lambda. Okay, so we have lots of examples. We have one module for each lambda and h star. Okay, so then when we were doing simple Lie algebras, what was the next interesting question you asked? So you said, well, supposing you took lambda and p plus, what did we say yesterday? We said that the corresponding V lambda, so for the moment let me assume G is simple. So if I took lambda to be dominant integral, then we proved a result which says that V lambda is finite dimensional. Right? So the principle is that if you take a dominant integral weight, something very interesting happens to the quotient. So then of course you want to ask, is some statement like this true for Kac-Moody algebras? If I take a dominant integral weight, is my representation somehow different and interesting? Right? So then the natural question, what happens if lambda is in P plus for Kac-Moody algebras? And the answer is a lot of very interesting things happen over there. But for the moment, the first thing that happens, so you could ask, do you get the similar thing that V lambda is finite dimensional? Okay, so that is too much to ask. So what it gets replaced by is the notion of an integrable representation. So definition, we say a GA module V is integrable if our generators act locally nilpotently on V. So what locally nilpotent means is, if you take any element, so if V is in V, then xi plus to the rv is 0, and xi minus to the rv is 0 for r sufficiently large. Okay. And r will depend, of course, on both v and I. I'm not claiming, you can get rid of the dependence on I, but not on v. Okay. So so then the theorem is that, so the theorem, which I think I'll refrain from too many attributions, but I think this theorem goes back to Katz and Lepowski and so on. And the theorem is that V lambda is integrable if and only if lambda is dominant integral. So this is the analog of the theorem which says, for simple Lie algebras, which says that V lambda is finite dimensional if and only if lambda is dominant integral. Okay? And this is what these I'm going to say a little more about this, but anyway, these are what are called positive level modules, which show up all the time in physics. Okay? These are, and this is what is connected with vertex operator algebras and so on. It's a study of these modules. Okay? So we'll say a little more about it. So now what do we have? So we now have G as an adjoint representation. Okay. And we have our modules V lambda with lambda dominant integral. Okay? These are the two families. This is one example and this is the other. Yeah? Why am I making a difference? Now supposing G is simple finite dimensional. Then, of course, the adjoint representation is simple, is irreducible. Yeah? And so this example is actually not distinct from this. Once it's irreducible, it must be one of these, right? Because it's finite dimensional. In the Kac-Moody case, this is not so. So in the Kac-Moody case, so GA is infinite dimensional. Then GA is never isomorphic to V lambda for any lambda in P plus. Okay, and the reason for that is essentially the lemma that I told you, and so the reason is that you don't have a maximal, so you should, at least a more advanced graduate student should be able to prove that essentially the reason for this is that does not exist a highest root with respect to our partial order. So the question you should ask over here is, so I'm saying if G is simple and finite dimensional, the adjoint representation is irreducible. Correct? If it's irreducible, it must be a V lambda. What lambda must it be? So it's exactly that lambda equal to theta, right? And what I'm saying over here is because you don't have a theta, this is not going to be a V lambda. Okay? So this is a completely different beast from the positive level, from the V lambdas, right? So then it's a natural question to ask. Well, do you have other examples? So question. Are there other examples of representations like GA, whatever this means, right? Like the adjoint representation, right? This is a very poorly formulated question, but still you want, I mean, is it a one-off? Is there something else? Is it part of a bigger family? Is there any interesting representation theory? So, and the answer is, I don't know if it's in the general Kac-Moody case. So I don't know how to answer this question. So the answer, I don't know how to formulate is, so don't know how to formulate a sensible question. No. So certainly I'm very far from being able to tell you anything interesting. Sensible question in the general Kac-Moody case. I don't know what it means to say like GA, right? I don't know what characterizes it or anything. So this. Yeah.
I don't know if you mentioned it already. GA is integral.
Yes, I didn't say that, did I? Yeah. Thank you. And is integrable. So, thank you. So why is it integrable? What would make it integrable? Right. So I have to say that if I take any element in G, and so if I, so if I take an element x in G, I have to say that add x, I power r x equal to 0, for instance, add xi plus for all r sufficiently big. So now what is built into my definition of the Kac-Moody algebra are Serre relations, right? And what do my Serre relations tell me? Well, they don't tell me this for an arbitrary x to begin with. They tell me this x equal to xj, right? But my x is built up by taking repeated commutators with xj. And so I can force this to happen. Okay, so it's an exercise. So the exercise is Serre relation, give this for x equal to xj, deduce for arbitrary x. Okay, so I would still, so it's still obviously not a satisfactory situation. One can't say what this means. But that's life because you don't know much about Kac-Moody algebras in general. But there is one case when we know a lot about Kac-Moody algebras, and so that's affine Kac-Moody algebras. So this is okay. So why are affine Kac-Moody algebras very good? Let's look at how we define. So I'm always going to stick to the untwisted case. It's not that nothing is known in the twisted case. It just introduces a different level of technicality. Nathan can tell you about the twisted case. Okay, so how did we define the Cartan matrix in the untwisted case? We had an underlying simple Lie algebra G, and then we did something fairly simple. We put its Cartan matrix here, and then I stuck in these numbers over here, and this theta was the highest root. And there was something similar here, which was minus 2 theta alpha I. So if you look at this, this entire matrix is really defined by knowing G, right? So it wouldn't be unreasonable to hope that the envelope, that the, yeah.
Probably want theta.
Theta, yeah. Mm-hmm. So it wouldn't be unreasonable to hope that the associated Lie algebra, affine Lie algebra, is related to this Lie algebra G, right? It's when you have so much control of the Cartan matrix, you should expect to have control of the Lie algebra. And so that is what makes the affine case tractable. You have an explicit realization of the affine, explicit realization of the affine Kac-Moody algebras. So generators and relations are nice enough for many purposes, but not all. So this dual realization that we're going to talk about, this second realization is what makes life good. So here's how you construct. So G will be my simple Lie algebra from now on. A will be its Cartan matrix. And I'm going to tell you A hat will be this matrix that I have over here. Okay. And I'm going to tell you how to construct G A hat. So here's the construction to begin with. So we're going to define L of G. I'm going to call this the loop algebra. This is G tensor CTT inverse. You take the Laurent polynomial ring in one variable, L loop algebra. Okay. This has an obvious Lie algebra structure. And now I'm going to deform the Lie algebra structure on this loop algebra. So I'm going to look at the following. I'm going to take L of G. I'm going to give myself a central term. And I'm going to give myself a derivation D. Okay. So let me call this G tilde for the moment. This is as vector spaces. And I'll define a commutator on this. So if I take x tensor t power n, y tensor t power m, the first term will look exactly like what I had up there. So this will be x bracket y tensor t power n plus n. But I want to deform this bracket. So I want the center to come play a role. So I'm taking a 1 cocycle. So this is plus n times delta n minus m. Kappa, this is a killing form, xy times c. Okay. So there is a correction term to the, okay. Kappa is the killing form. And what is this? So, and what is this D? D is going to act on x tensor t power n as a derivation, so it's just n times x tensor t power n. If you like, D is just the derivation td by dt on this. Okay? And then the C is central. So it's an exercise to check that that's a Lie algebra. And the theorem is G tilde is isomorphic to the extended affine Kac-Moody algebra, A hat. So in this algebra, everything is given by generators and relations. Here you can calculate everything in terms of G. And how is the isomorphism given? So I'll define it this way. This algebra has generators xi plus or minus. So this A hat is going to be, this extra node is usually called 0. This is your n by n matrix, and this is, okay. So the xi plus for 1 less than or equal to I less than or equal to n will go to x alpha I tensor 1 plus or minus. And my extra Chevalier generator will go to x. So what should I put over here? What I put over there should obviously, so these things just used up my alpha i's, right? What I should put over here should somehow involve my theta, because that I haven't used so far. And in fact, it should involve minus theta, because of this minus sign that I have over there. So in fact, the correct thing to do is to take x theta, but you take minus or plus, right? Now, I obviously don't want to take 1 over here, because if I take 1, I'm not going to get anything bigger. I'm not going to get my entire loop algebra over there, for instance. So what I take is t plus or minus 1. The HIs, well, what does the HI go to? So for 1 less than or equal to I less than or equal to n, it will go to HI tensor 1. And H0 will go to minus h theta tensor 1. But not that, I have to allow for my central term, so I'll control my central term with a C. I have to remember when I was doing my definition of the Kac-Moody algebra, I had to give myself an extra generator, right, which I call D1. And I have to give myself only 1, because n plus 1 minus rank A in this case is equal to 1. And so this D exactly goes to this D. What I call D1, I only have to add on a D1, and that D1 goes to D. Okay. So this is the theorem. So this is how you explicitly realize this very abstract algebra in a very concrete way. Okay. And now let's see that you can answer many questions that I was raising earlier. So So what are the roots? So now let's talk about the roots. So what will the roots be? So the roots of the affine algebra, so this is again just meant to be very quick. A root is supposed to be an eigenspace for the Karsen subalgebra. So the Karsen subalgebra here will be HE equal to H tensor 1 plus CC plus CD. And what you can check is, yeah. So you can check that G alpha tensor T power n is an eigenspace for HE with eigenvalue. So I want to just write down the eigenvalue. I'll call it alpha plus n delta, and delta is 1 and delta on H divided CC. Okay. So just take it for granted, just let me assume this. What does this tell us? So supposing you believed that this was an eigenspace, that it was a root space, what is the dimension of this space? It's exactly the dimension of G alpha, which you know is 1, right? So we're happy with this dimension. But there's one more kind of space that we have that we should worry about. Yeah. Yeah.
Theta should be 2 for that. The killing form should be.
Yeah, the killing form is normalized.
Is normalized.
Yeah. That's right. So we'll normalize the killing form so that kappa h theta is 2. Or, yeah. So there's one more eigenspace. So if you look at H acting on H tensor T power n, okay, HE, you'll find that this acts via n delta. Okay, so let me write this intelligently. So HE, H tensor T power n, has eigenvalue n delta. I've defined delta over there. So again, assume that you believed me. So then what is the dimension of this eigenspace? The dimension of this eigenspace is exactly the dimension of H, which is usually more than 1 for a simple Lie algebra, right? So the dimension of H tensor T power n is equal to the dimension of H. In other words, for affine Lie algebras, you know all the dimensions of all the root spaces. Okay, so this concrete realization is very helpful in making everything very explicit. Okay. So now let's see if I can at least formulate an intelligent question as to what does my representation, the adjoint representation, look like. Okay. Yeah. So we already saw that if you had V lambda with lambda in P plus, right? So I want to, I shouldn't have done that. Okay. I want to make, no, I think I'll do it more systematically. I'm going to make a definition. So definition. We'll say that a representation, so we'll say that, am I ready to make this definition? No, I'm not. So I need a lemma, which you know, but it's just helpful to restate it again. So lemma, V is an integrable representation of GEA, implies that the eigenvalues of the HI are all integers. So why do I think you know this lemma? So I think you know this lemma for the following reason. So let's look at this xi plus or minus and the hi's. Yeah? We know that this forms an SL2. And we know that if you take any vector over here, this gives you a finite dimensional SL2 module. That's a definition of integrable. Okay? And I said yesterday that on any finite dimensional SL2 representation, the eigenvalues of the h's are all integers. So you know this. Okay? So in particular, what is C now? If you remember now, C in this explicit realization that I wrote is actually equal to h0 plus h theta acts as integers on integrable representations. Okay? So that motivates the following definition. So we say that it's a definition. An integrable representation is said to have level L, K, although L might be more natural, level K, if the center acts as K times the identity. On the representation V. Okay? So that's the definition of level. So if you look at V lambda, what is its level? So the level is lambda of C, which is equal to lambda of H naught plus lambda of H theta. Okay.
So what you said here is really that all the eigenvalues of C are integers.
Correct.
Now your definition of integrability, you want it to act as some multiple of the identity.
That is what that's when you say it has level K. Right. I'm going to now state a lemma which says that for the most part you can write integrable. You can always write these integrable representations as with some small restriction as a direct sum of things of different level, so you can focus your study on a particular level. So, but so this is equal to this, and this is going to be greater than or equal to 0, and in fact lambda C is equal to 0 if and only if lambda is equal to 0. So these representations that I constructed by doing my Verma module and then going to its irreducible thing are all examples of positive level representations, except for the trivial one which has level 0. Okay? So the level 1 representations are what appear most often, and those are called the basic representations. So the level 1 representations are particularly important and well understood through these Heisenberg algebra constructions. Higher level representations are not. So even level 2, I think, is sort of quite hard to do. So now let's look at my example, my favorite example of the adjoint representation. Remember, I'm trying to get some abstract idea of what it might be. So I have my adjoint representation of GEA. So what do you think it's? So I claim that this has a level, and what do you think its level is? So for the level, what do I need to know? I need to know how the center acts on it, correct? How does what is the adjoint action? Well, this is the center, so it acts on it as 0, right? So finally, I can say, what is a rigorous statement I can make? The adjoint representation is an example of a level 0 representation. And so I can now ask, are there other examples of level 0 representation? So I've given meaning to the word like the adjoint representation eventually. So now I can ask the question, are there other examples of level 0 representations? Okay? And if you're a representation theorist, what is a natural question to ask then? So another natural question, once you form, actually a more general question is, classify irreducible integrable representations of arbitrary level. It doesn't have to be of level 0. Okay? So I think this is where I will stop today and sort of continue from this point tomorrow to talk about how one might approach classifying these representations and what's. Okay? So, thank you.